rational functions and Ratey. The parent function for rational functions is f of x equals 1 over x, and this is its graph. So the graph is quite funky. It's not something you're used to, I'm sure, but it introduces some new terminology called asymptotes. An asymptote serves as an invisible boundary line that the graph approaches but doesn't touch or cross. So on the parent function, it has a vertical asymptote, basically where the y-axis is, and it also has a horizontal asymptote where the x-axis is. Vertical asymptotes have equations, so if it's a vertical, it would start with x equals. If it was horizontal, it starts with y equals. The domain for the parent function and the range are all non-real zeros. So how to express that with symbols, it would look like this. You could say negative infinity to 0, a U for union or and then 0 to infinity. And you would write it like that because, again, you can't include 0, and there's like a little pause or break wherever there's an asymptote. So that's how you would write the domain or the range in this particular case. And then there's a general format for rational functions that has a over b times x minus h plus k. So we've seen the h and the k before, and we've also seen a. H is still a horizontal movement, left and right. K is still a vertical movement, up and down. A will determine if it stretches vertically or compresses or shrinks vertically. B will determine if it compresses or compresses or stretches horizontally. So make some quick little notes about this basic format because you might see it again. We're not going to spend too much time on it in this lesson, but it's just a good FYI to make note of. And then another tidbit is this little study tip about when they transform, the reciprocal functions and the asymptotes move in the same manner as h and k, and h and k will be the intersection of the asymptotes, the vertical and the horizontal. One second. Alright, so now we're going to practice graphing rational functions using the Ratey method as well as a graphing calculator. The Ratey method is listed on this handout here. It's an acronym, and it tells you what each part stands for and how each part applies to the rational function. So the first thing we're going to find are the roots for R. Roots are your x-intercepts. To find the roots, the directions say set your numerator equal to 0 and solve. And then you write your answers as points, number, comma, 0. So let's find our roots. So for our numerator, it's just x. We equal it to 0 and solve. Solve means get the variable by itself. X is by itself, so I'm already solved it. And then you write your solution as a point. So it'd be 0, comma, 0. At the same time that you find each piece, go ahead and apply it to the graph. So here's 0, 0. That's our root. We're going to label it later. Now let's talk about A. A is for the vertical asymptotes. To find the vertical asymptotes, you set the denominator equal to 0 and solve. You write your answers as lines, x equals number. So in our denominator, we have x plus 3. We equal it to 0, and we solve. To solve, we're going to have to subtract 3 on both sides. So x would be equal to negative 3. So this is our vertical asymptote. So negative 3 is over here. Draw a dashed line to represent our vertical asymptote and label it x equals negative 3. P is for special squared terms. And then it provides some examples of what a special squared term looks like. So x squared alone is a special squared term. Negative 2x squared alone is a special squared term. If you have a parentheses with a power of 2 attached, that's a special squared term. And if it's not, or if it doesn't have any squared terms, then it's not a perfect squared term. So on our example, we don't have a perfect squared term in the numerator or the denominator, so this does not apply to us. So we'll just put NA. In behavior, we look at the first terms, and we got to determine the ratio of the first terms or the degree of the first terms. So it would either be balanced, top heavy, or bottom heavy. Balanced if both degrees for the first terms are the same. Top heavy if the degree on top is larger. And bottom heavy if the degree on bottom is larger. So I would take the two terms, x from the top and the bottom. X at the top has a power of 1, x at the bottom has a power of 1. So this is what we call balanced. And since it's balanced, we got to find the horizontal asymptote by putting this as y equals and reducing. And we practiced this just a couple of days ago, that if the same things are on the top and the bottom, they cancel each other out and make a 1. So the y is equal to 1. That is our horizontal asymptote. So that is up here above the x-axis. And label it. And then y is for your y-intercept. So we're going to plug in 0 for x and find our y-intercept. So y is equal to 0 over 0 plus 3, which is the same thing as 0 over 3. So 0 divided by 3 is 0. So that means our y-intercept is 0, 0. So our y-intercept and our x-intercept are the same point. Now, all we have to do is draw our curve. According to the guidelines, you have to pass through the x and y intercepts. So that's where I'm going to start. And you want to get close to your asymptotes, but not past them. So that's one piece. Based on the parent function was broken into two pieces. So most of these functions should be broken into two pieces. It is possible it could have more than two, and it's possible to have only one. So you just got to be very careful. And again, I'm going to label my points on my graph. Now to find the other piece, we can use the graphing calculator. But it's actually a puzzle. And the reason is, most of the time, if ever, you don't put pieces on top of one another. So that eliminates this top little quadrant up here. So it's either going to go, as I was saying, So this top little portion is automatically eliminated. So it's either going to be the top left or the bottom left. Now, if we had a special squared term, it possibly would have been the bottom left. But because we didn't, that only eliminates and leaves the top left. All right, and if you want to check it on the calculator, you're more than welcome to, or trust me and believe me. So in our equation, we're going to type alpha y equals 1. So we're going to put x over x plus 3. And a standard window is perfect. Graph. And there we have it. So as you can see, it's getting close to 1, but it doesn't cross on both ends. Now let's talk about the domain of this particular graph. So when we talk about the domain, as we read from left to right, we have to, whatever number represents our vertical asymptotes, we have to use those in the domain. So we always start at negative infinity. And then as we go from negative infinity, we approach negative 3, but don't touch it, remember? So negative 3 is the number we need to use in our domain. And then it starts at negative 3, but on the other side. So we use our u for union, and then negative 3, and then if you trace the piece, it keeps going to positive infinity. I'm sorry, I wrote a negative infinity, and I should have written a negative 3. All right. Again, it starts at negative 3 all the way to positive infinity. So that's the domain. The range, again, range is from the bottom to the top. So at the very bottom, again, it's negative infinity because it continuously goes downwards. And as we go upwards, it approaches 1, but doesn't touch. So that's why, even though 1 is a number, because it doesn't touch it, is why we use parentheses and not brackets. So you're always probably going to use parentheses when writing this domain and this range. And then I need my union. Starting back at 1 is where this other piece up here starts at, and if you notice, it goes upwards forever, so to positive infinity. And there we have our first graph. Let's try another. Now, let's again remember that R stands for the roots, so you take your numerator, which is 5, and equal it to 0, and solve. Solve means get the variable by itself. There are no variables in my numerator. So when there are no variables, there are no roots. So no roots. A was for your vertical asymptotes. You take your denominator, in this case it's x minus 2 squared, and equal it to 0. Remember, to get rid of a power of 2, you have to apply the root, the square root, or the reciprocal power. So that would be x minus 2 by itself, and the square root of 0 is 0. Now, add 2 to both sides, so you would get x is equal to 2. That's our vertical asymptote. So let's graph that. That's on the right side. T is for special square terms, and I do see a parentheses with a power of 2 attached, so yes, there's a special square term, and it's on the bottom. So let's go back and look at our handout and see what it means when it's on the bottom. When I have a special square term on the bottom, that means the pieces will come together at the vertical asymptote. The pieces will come together at the vertical asymptote. So, gotta remember that it's going to come together. So I usually I usually will put a T by my vertical asymptote to remember that it's going to come together. All right, E is for end behavior, and that means we look at the first terms. So the first term, the only term of your numerator is 5. The first term of the denominator has to be found by actually carrying out the multiplication. So let's do that. If you recall, when you square something, that means to multiply it times itself. So that means we need to multiply x minus 2 by itself. And then you use the box or FOIL to multiply. So you would get x squared minus 4x plus 4 when done properly. So that means the first term of your denominator is x squared. And so the degree of my numerator is 0 because I don't have any variables. The degree of my denominator is 2. So that means this is bottom heavy. So I would put BH for bottom heavy. And anytime it's bottom heavy, according to the handout, the horizontal asymptote is at y equals 0. So y equals 0 is your x-axis. So since it's already there, just extend it and label it so that you don't forget that it won't touch. Now to find the y-intercept, remember we place all your x's with zeros and solve. You can use either version. You can use the original way it was written, or you can use the expanded form. You're going to still get the same result. So that's 5 over negative 2 squared, which is 5 over 4. And write it as a point. 0 always leads for a y-intercept. So it would be 0 and 5/4. And which is the same thing as 0 and 1.25 for those who like decimals. So that's about here. You don't have to turn it to a decimal. You just have to put it in the approximate location. I like fractions just a little better. All right, so the only point I have to work with in this particular function is that y-intercept, and the graph has to go through it. So that's where I would start, in the top left. So again, I want to approach my asymptotes and not touch them or cross them. So that's the top piece. Now the second piece, again, in this situation, we're not going to use the bottom left because, again, most of the time, if ever, the pieces are not together. But remember we had a special square term, and it says it's going to come together at x equals 2. So since it's going to come together, that means they're going to go in the same direction at x equals 2. So it would look like this. I would have to put it in the top right. Only because I said it comes together. So they should meet up at the line and then go in the same direction. That's what it means when it comes together. And then again, you could verify with a graphing device if you don't believe me. I want you to practice number 3 on your own. Let's do number 4 together. And then the others you're going to do on your own. So again, let's find our roots by taking the numerator and equaling it to 0. So add 4 to both sides, you would get x equals 4. Write it as a point. So that would be 4, 0. And plot it and label it. A is for your vertical asymptotes. So in this case, we would have to either A, use the quadratic formula, or B, factor it. I'm going to choose B, factoring. It's a trinomial, so that means I can use the X method. And 9 would go at the top, 6 would go at the bottom. 3 times 3 is 9, 3 plus 3 is 6. So those are my factors. It would be x minus 4 at the top, and x plus 3 times x plus 3 at the bottom. And we just kind of did something like that. When you have the same thing duplicate, it can be rewritten with a power of 2. So that's going to be important later. But now, I need to find my vertical asymptotes by putting my denominator equal to 0. And since they're the same expression, I only need to take one of them and subtract 3 on both sides. So I would have x is equal to negative 3 as my vertical asymptote. So that's over here. And then t was for special squared terms. And when I rewrote it, x plus 3 had a power of 2 because it appeared twice. So it's on the bottom. Again, it's going to come together at x equals negative 3. So put a t to remind ourselves. E is for end behavior. So the first term of my numerator is x. Second, the first term of my denominator is x squared. The degree up top is 1. The degree on the bottom is 2. So this is bottom heavy, which means there's a horizontal asymptote at y equals 0. Again, your y-axis. So extend it, or x-axis, and label. Now our y-intercept, replace all x's with 0. You can use any format or version of the equation that you desire. You can use the end one, or the first one, because it'd be 0 plus 0 plus 9. So at the top, it would be negative 4. At the bottom, it's 9. So that means it's negative 4 over 9. If it was something that I could reduce, I would reduce, but I cannot. So write it as an ordered pair, so 0 and negative 4/9, and plot it. So that's here. And we're going to label it. Now we're going to graph it. And this one is kind of strange because we have a y-intercept and an x-intercept, and our x-intercept is on our horizontal asymptote. Pretty tricky. Remember, we told you asymptotes you're not supposed to touch. But there are certain circumstances where you do touch horizontal. However, listen clearly, a graph will never touch a vertical asymptote. Again, this is a rare case where we touch a horizontal, but we will never touch vertical. So there's that piece. It doesn't touch and come back. That's just my pen. Now for the second piece, it's either going to be top left or bottom left of my vertical asymptote. But remember, we're supposed to come together at the vertical asymptote, so that means it must go on the bottom. There are no x-intercepts on this side, so that means it will not pass the asymptote on this piece. So this is how it looks. So these graphs are quite funky, believe it or not, but you can handle this. I will show you the remaining equations so that you can graph them on your own. But other than that, we're pretty much done. This is number 5. And that's number 6. This concludes the lesson for today.